Good morning. This time we will concentrate on the hovering flight blade element theory. I recap here the main formulas that we obtained in the actuator disk theory. Induced velocity in hover, induced power, figure of merit, disk loading and power loading. Momentum theory provides a good general explanation of hover power, but in getting a good understanding of hover, one needs to analyze what is happening at the level of the blade itself. This picture is important in the blade element theory. On the left-hand side you see the rotor from up with a blade and a blade element on it at a radius r. The blade is rotating with an omega r velocity. It is rotating counterclockwise. Induced velocity is entering in the plane of the rotor and the blade is assumed at an azimuth angle C. The blade profile, you see the total velocity and the angles of all this blade profile. Induced velocity composed with the omega r rotational velocity of the blade gives the resultant velocity on the blade element, Vr. The following angles can be defined. The angle of attack, alpha, is defined as the angle between the velocity vector and the zero lift line. The inflow angle, phi, is defined as the angle between the rotor plane and the velocity vector. The angle of attack, the pitch angle, is defined as the angle between the rotor plane and the zero lift line, theta. One can see that we have the notation of TPP, which stands for tip puff plane. What is the tip puff plane? The tip puff plane on a helicopter or the disc plane is defined as the plane formed by all tips of all blades in a helicopter. The resultant rotor force is perpendicular to the tip puff plane in an equilibrium flight. Going back to the helicopter blade element, one can write the lift and drag force dl and dd on the blade element and project these forces on the rotor plane, on the tip puff plane and perpendicular to the tip puff plane. In this way, one obtains the thrust force on the blade element and the drag force on the blade element. The thrust force can be approximated with the lift force on the blade element. This is because the inflow angle is small and the drag is also small on the blade. The power required for hovering is then the product of the drag force in the tip puff plane multiplied with the velocity, which is Vr. However, induced velocity is much smaller than omega r, so we are going to use omega r as the final velocity. Substituting the expression of the drag force into the tip puff plane and making the calculation, one gets that the power on the blade element is a product of thrust and induced velocity plus drag multiplied by omega r. The first component is the so-called induced drag, which is the rearward component of the lift. Therefore, don't forget, induced drag is caused by the generation of lift. The second term is the so-called profile drag, the result of air friction acting on the blade. Integrating along the rotor radius from 0 to r and multiplying with the number of blades N of the rotor gives us the induced power and the profile drag power. This will result in a hover power for the helicopter. One can see that the tail rotor power is not included. As an exercise, you will have to make yourself the integration to be convinced on the results that we have obtained here. The induced power is defined as the power needed to overcome the blade's induced drag. It is number of blades multiplied with the integral from 0 to r from thrust on a blade element multiplied by the induced velocity. This integral cannot be solved analytically because induced velocity is varying along the radius, but also because it is non-uniform on the whole rotor. Usually we approximate this power as K, a factor, correction factor, multiplied by ideal power. So the induced power final expression is KTVI, with K a correction factor between 1.1 and 1.2. Profile drag power is the power needed to overcome the blade's profile drag. One can calculate the integral of these drag forces multiplied with omega r. Assuming a medium drag coefficient CD bar on the rotor results in the performing the integral and gives us the final profile drag formula. One has to define the so-called sigma rotor solidity. The rotor solidity is a design parameter and it is defined as the ratio between the solid area of the rotor and the total area of the rotor, NCR divided by PR squared. It is a key design parameter that measures the amount of power that can be used by the rotor. So, in order to have a good hover, one should have a small solidity. In order to have good performance and agility, one should have a large rotor solidity. The values of this solidity are varying as a function of the rotor diameter between 0.05 and 0.15. Here you have the graph for different helicopters. You see there the Robinson R-22, the Chinook CH-47, the V-22 Osprey and other aircraft. Going back to the integration, we see that the profile drag power can be calculated. Then, the total power required for a hover in the blade element theory is a summation of the induced power and the profile drag power, and is given by this formula. The figure of merit can be calculated also in the blade element theory by approximating ideal power with the induced power and the total hovering power, writing it as induced plus profile power, we obtain the figure of merit in the blade element theory. How to design a good rotor? Assume that one has two rotors developing the same thrust. One rotor has higher disk loading, so small rotors. In this case, they will have a higher induced velocity. The lift will be tilted further back and it will induce a larger induced drag. So it will have a higher figure of merit. Recalling the power loading formula from the actuator disk theory, we can conclude that One can claim a higher figure of merit by designing a rotor with a higher disk loading will result in lifting less for a given power. This is the end of the explanations of the formulas related to the hovering blade element power.